Guys, I'm recording it, I'll post it under the help sessions link. So you know on the website there's that help sessions link. So I'm having these weekly help sessions for people. What's my goal this semester?
No C's.
No, not no C's. No D's or F's. I'll be okay with no C's too. But I really like to have no D's or F's this semester. And you know, y'all did well on that first test. I know that not everybody did as well as they'd like, but the average on that first test was a lot higher than it's been in the past. So I'm very pleased. I think y'all are probably smarter than other students that I've had. Y'all are probably the smartest students I've ever had. My entire life. What? No, I think. All right. So remember, there are these topics. We're doing chapters 2B. That's the second part of chapter 2. That's capacitance. So we have capacitance. I sent an email out with all these different topics, but these are the particular topics that you have. Capacitance and capacitor circuits in series, parallel, and combination. And then we have current, resistance, power, Ohm's law. You've had quizzes on all these different topics, by the way. Resistors in series, parallel, combination circuits. That's when they're in series and parallel together, and then household circuits. I think you had about 8 or 9 questions from these topics, and then the rest. There are a total of about 26, I think, or 27 from all those other topics. Okay. Let's just go over all of these. Is that okay? I'm going to step through all of these. And then if you have particular questions, please feel free to stop me. Or if you don't want to stay, that's fine too. All right, so for capacitance, we had a couple things. We know that Q is equal to CV, and that C is equal to kappa epsilon naught A over D. Remember that kappa is that dielectric constant. When you put a dielectric inside of a capacitor, it increases the capacitance. We had a series of concept test questions about these things, so make sure that you go back and review those. I don't think they're online right now, but as soon as I get back to my office, I'm going to put them online. It's okay, I'm sorry. So be able to calculate the charge, and then also be able to calculate the capacitance. And then if you change the geometric dimensions of a capacitor, make sure you know how that changes the capacitance. So for example, if this increases, this decreases, for example. We also, if I change the capacitance, note how that changes either the charge or the voltage. So if my capacitance decreases, that means my voltage increases. All right, we also have capacitors in series. Don't forget the rules that we have for caps in series. For capacitors in series, the equivalent is equal to 1 over C1 plus 1 over C2 plus however many capacitors you have. Capacitors in series have the same charge. Capacitors in series, Q equals CV. And for capacitors in series, the voltage equals V1 plus V2 plus ... Now these rules are a little bit different for resistors, right? Resistors in series. But fortunately on the test, the first few questions will be about capacitors, and then everything else will be about resistors. So you'll be able to shift gears on the test. All right, so for example, if I gave you a circuit with capacitors, say 12 volts, 3 microfarads, 6 microfarads, something like that, you should be able to tell me what is the voltage and the charge on all of these. Hopefully you can look at it right now and sort of tell me. We've done this problem several times. What's the voltage here? 8 volts. Remember, with capacitors, the smaller capacitor has the bigger voltage. All right, so the 3 microfarad has 8 volts, and the 6 microfarad has 4 volts. I know that it's 8 and 4 because one splice the other. The capacitance is here on a 2-to-1 ratio, or rather a 1-to-2 ratio. And I also know it's 8 and 4 because that adds up equal to 12. So I know that I have 8 volts here and 4 volts here. Another way that you could do that if you forget is you can find the equivalent capacitance. A 3 and a 6 in series is 2. Don't forget those fractions. I'll give them to you again just to remind you in just a second. So 3 and a 6 is 2 with a 12-volt capacitor. Since Q equals CV, 2 times 12, that's 24 microcoulombs. So I have 24 microcoulombs here and 24 microcoulombs here because the capacitors in series have the same charge. All right. Let me go ahead and give you those fractions. 1 over 1 over 3 plus 1 over 6. This is equal to 2. 1 over 1 over 3 plus 1 over 3 plus 1 over 3. That's equal to 1. 1 over 1 over 4 plus 1 over 4. That's equal to 2. 1 over a half plus a half. That's equal to 1. And 1 over 3 plus 1 over 6 plus 1 over 2. 4 plus 2 plus 6. Yeah, that's equal to 1. So I use these common numbers just to make it a little easier on you, not dealing with decimals and stuff. All right, for capacitors in parallel, I have similar rules. I have the equivalent. They have the same, excuse me, what's the second rule for capacitor? Oh, they have the same voltage, yes. Have the same voltage. Q is equal to CV. And then, we don't really use this one, but the equivalent charge is equal to the sum of the individual charges. That means whatever charge I have on that equivalent charge, adding up all the capacitors in parallel, they should add up to equal that. All right, you should be able to look at the capacitors in parallel and tell me what are the charges and voltages on them. So, for example, here, I have a 2 microfarad, 4 microfarad, 12 volts. You should be able to tell me what is the equivalent, first of all. It's 2 plus 4, that's 6. I have 12 volts here, 12 volts here, and then you should be able to tell me the charge on each of these. I think y'all can do those, right? Y'all good on those? You could also see a combination circuit. I'll do a quick example. I go down from here. If I'm going too fast, let me know, but there's a lot of material, so I'll be able to cover it all. Let's say I have a combination circuit like this. Let's see, I could add one more capacitor like that. No RC circuits, that's resistor capacitor circuits, and no multi-loop circuits. Multi-loop circuits, you'll know them because they have multiple loops and they have 2 or more batteries. So look in your homework. I think there's 1 or 2 multi-loop circuits. You're not doing those for Chapter 4. And then also not doing RC circuits. So if they have a resistor and a capacitor, you're not doing that. All right, so here, to find my equivalent, I would combine these two. I already know a 4 and a 4 is 2 microfarads. And then I would combine this 2 and this 1. That gives me 3 microfarads. And then I have a 3 and a 6 in series. I'll go ahead and draw that. 6 microfarads, 3 microfarads, 12 volts. All right, I've already done this. So 3 and a 6 is a 2 microfarad. So be able to find the equivalent capacitance. This equivalent capacitance would be 2 microfarads. This would be 4 volts, and this would be 8 volts. Remember, bigger capacitance has a smaller voltage, and vice versa. All right, so they're inversely related. That's not the same for resistors. So if I have 6 volts, 4 volts, and 8 volts, that means I have 4 volts here. I have 8 volts here. And what voltage do I have here? Not 8. I have 4, right? I have 4 volts on this capacitor and 4 volts on this capacitor. These are identical capacitors, so they split this 8 volts evenly. Right? I know that that voltage has to add up to equal 8 volts, because I have 8 volts across this branch and 8 volts across this branch. But these individual capacitors split up at 8. Right? So because they're identical, I get 4 and 4. So you can see a combination circuit sort of that difficulty, not about that difficulty or simpler. Okay? I think y'all can do those, right? Y'all good to go on those? All right. The next topic had a bunch of stuff about current, resistance, power, and Ohm's law. All right, you need to know current. The definition for current is I equals Q over T. Be careful. Know that this has to be in seconds. We've had a couple problems where we have to actually find the amount of charge given the current for a circuit. But I'll forgive that time in minutes just because, I don't know, to be honorary or whatever. But don't forget the SI unit for time is in seconds. So make sure you convert that to seconds. Ohm's law, V equals IR. Simple. I mean, you need Ohm's law, of course, for all the circuits and stuff. But you could just have a basic Ohm's law problem. You know, I have a circuit. I have 12 volts. I have 2 ohms. What is my current? My current there would be 12 times 2, I times R. Or excuse me, no, my current would be V over R, 12 over 2, which would be 6 amps. All right, and then further I could go on and say, well, in 2 minutes or 3 minutes or whatever, how much charge has passed, in which case you'd use this definition for current. Okay, we also have power, and a whole series of questions about power. Remember we had these different expressions for power, I squared R, V squared over R, and asking about when is the power greater for a particular situation. The reason you would use some of these is, like if we're comparing two objects, say 2 resistors that are in series, 2 resistors in series have both a different voltage and or they have the same current, but they have a different voltage. Well, that's not a very good example. Let me think of it. If I have 2 resistors that have different voltages, never mind. Let's do an example. Okay, let me show you an example. We had some problems like this. So say, for example, I have 2 resistors in series, and I just want to know the power that's distributed across them, the power that's given out of those. Let's say that I have 2 ohms, and I have 4 ohms, and I have 12 volts. All right. I could find the power in a couple different ways. I could find the power by calculating what is the voltage and what is the current in those resistors, and then I can figure out what is the power. Y'all follow me on this? Yeah, sorta? No? All right, so here, for example, I know that I have to have 2 amps on both of these. So I could say I squared times R, so my power here would be 4 times 2. I squared times R, so I have 8 watts, and here it would be I squared times 4, so that would be 16 watts. So just be able to calculate the power given a particular device. And then also know that devices that have a greater power rating, do they have a bigger or smaller resistance? If a device puts out more power, does it have a bigger or smaller resistance than the one that has less power? It has less resistance. Something that puts out a lot of power, like your hair dryer, it has a very, very small resistance. It's basically just a piece of wire that you put electricity through. All right? So look back at the concept test. There was a whole string of questions about power and devices that we use. All right. Let's see, power, Ohm's law. Then we have resistors in series and parallel. Listen, there are a lot of circuits on this test, so make sure that you're up to date on your circuits. For resistors in series, we had a similar set of rules. We had equivalent resistance is R1 plus R2. We had resistors in series have the same current. We have resistors in series, V equals IR. And the total voltage equals V1 plus V2 plus ... You could have just a question just asking you about resistors in series and how they act. Same for parallel. The equivalent. They have the same, what do they have the same of? That's right, they have the same voltage. V equals IR. That's your, and then the total current is I1 plus I2 plus dot dot dot. We're going to get these last two rules, by the way. This one and this one we'll use next week when we do the multi-loop functions, or multi-loop circuits. Okay, so be able to solve both series circuits, parallel circuits, and combination circuits. You'll have all of those. So for example, if I have a series circuit, let's say that I have let's just do 2 here. Let's say that I have 2 ohms here. I have 2 amps here. And 12 volts here. What is this resistance? Alright, well if I have 12 volts and 2 amps, that means that my equivalent resistance should be what? Because I'm getting 2 amps off a 12 volt battery, and it has to be 6 ohms. So if this is 2 ohms, then this has to be 4 ohms. Right. Simple series circuit like that, you'll have some that'll be similar to that. Just simple, what is the voltage or current across these resistors, or finding an unknown resistor like this. You could also have a simple parallel circuit. These are a little easier. Alright, so if I have a 12 volt battery here, a 2 ohm here, and a 2 ohm here. First of all, the equivalent resistance of this would be a 2 and a 2 is a what? Is a 1. 1 over a half plus a half, that's 1. I can also find the current. I would have 6 amps here and 6 amps here, because I also have 12 volts here and 12 volts here. So 12 divided by 2 is equal to 6. I is equal to V over R. So those are resistors in parallel. And then you'll also have a combination circuit. Maybe something like this. Alright, I want to know the voltage or the current across any one of these. Hopefully you can just look at this now and begin to make sense of what the voltages are. So here I have a 2 and a 1, which is 3, and then that's paired with a 6 in parallel, 2, and then I have a 2 and a 2 here. Right, 2 and 2 is 4. So what is the voltage here? If this whole thing is 2 ohms, don't worry, I'm going to write this down in a second. This whole thing is 2 ohms. What is the voltage here? No, not 3. It's 6 volts. Because I have 2 ohms and 2 ohms that share 12 volts, so I'm going to have 6 volts here. So what would be my voltage here? 6 volts. What would be my voltage here? 4 volts and 2 volts. Let me write all that down. Okay? So if I simplify this circuit, I have 2 ohms, three ohms, six ohms, and so that's a 2 and a 2, 12 volts. Alright, so these are identical, so I have 6 volts here and 6 volts here. That means I have 6 volts on this 2 ohm resistor. Alright, here I had 6 volts across these 2 resistors. That means I have 6 volts here and 6 volts here. And if I have 6 volts, if I sort of draw these up here, I have 6 volts, 6 volts. I have 6 volts across these 2 resistors, which are in series. If I have 6 volts across these 3 ohms, that gives me a current through each of 2, right? 2 amps. 6 divided by 3 is equal to 2. So I have 2 amps here and 2 amps here. 2 amps through this gives me 4 volts, and 2 amps here gives me 2 volts. Those sort of problems, if it takes you a little longer to go through them, that's fine. Like if you have to write out all the intermediate steps, I think you'll have plenty of time. But it'll help if you can just look at them and sort of think about how the voltages are distributed. Okay, what was the next topic? Oh, household circuits are the next thing. Household circuits, we had 3 safety features that you'll need to know the definitions of and be able to identify, and then also just sort of basic things about our household circuit. I think there were 2 or 3 questions about this. So a couple of things about our houses. Our houses are in parallel. All right, so the thing about parallel circuits is everything operates at the same voltage. As I add things in parallel, the voltage given to those different things does not change because the voltage is always the same as the source. It's always going to be 120 volts. Also, as I add things in parallel, what happens to the total current? It increases, it goes up. Okay, so houses are in parallel, so everything has the same voltage. And I total goes up as you add devices. I think that's all. And then we have the 3 safety devices, the GFCI, the ground, or the 3rd prong on your outlet, on your plugs, and then also circuit breakers. People often confuse these 2 because they sound really similar, but they serve different purposes. The GFCI turns off if IN exceeds I out. So you want to look for this inequality if I'm giving you a definition for GFCI. Remember, it measures the incoming current, and then it measures the outgoing current. If there is ever a difference between those 2, that means that current's going somewhere it shouldn't be.
What are the differences?
Oh, ground fault circuit interrupt. You need to know that too. I've asked questions about that before. Ground. Bless you. Fault circuit interrupt. It interrupts the circuit. You'll see that sort of ground fault circuit interrupt. All right, it measures those 2 currents, and if they're ever different, it turns the circuit off. It interrupts the circuit. The circuit breaker, on the other hand, it turns off if the total current, not the current for a single device, but the total current exceeds some capacity. Right? 15 amps, 20 amps, whatever your circuit is rated at, it will turn off if that current in the total circuit exceeds that capacity. So as you're adding devices, if you exceed that current, then it will turn off. So it's our circuit breaker. And the ground, this provides a clear path to ground. A clear or alternate path to ground. So remember, this protects us from faulty devices. If our device, computer or whatever, if a wire comes loose on the inside and the case becomes electrified and you touch it, then that electricity would go through you into the ground. But if it's connected to our 3rd prong in our outlet, it goes directly to that brass rod which is driven into the ground outside your home. So that's there to protect you against faulty devices. All right. Oh, and then also regarding the circuit breaker, we worked a problem like this. But I could ask you to find what is the safe capacity of a circuit. And we had worked through a couple problems. So say I have devices hooked up to a circuit, say 1200 watts, 480 watts, 360 watts. And then I add, say, a 600 watt device to that, and the circuit breaker goes off. Y'all remember these questions we did in class? Yeah? So here I have all these things operating okay. on my circuit breaker, but then I add this thing, and it kicks off the circuit breaker. And I ask you, what is the safe capacity of this circuit? You need to find the current. I know that I is equal to P over V, that's for my power definition, and that V in my household is 120 volts. So this one carries 10 amps, that's 1200 over 120. This is 4 amps, this is 3 amps, and this is 5 amps. So somewhere between 17 amps and 17 plus 5, that's 22 amps. Somewhere between those two numbers is where the safe capacity is, because it kicks off when I put in this 5 amps, and I exceed that total current that's allowed. So, you know, somewhere between 17 and 22, 20 maybe, or 18 or 19 or 21. All right, that's everything on the test. We can spend some time looking at questions. Y'all want to do that, at old test questions? Or any particular questions that y'all want to go over? Yeah. Yeah, we did this in the help session yesterday. It's good questions. So let's say that I have a circuit like this. The thing that gets people on these is that when I add resistors in parallel, the equivalent resistance decreases. And when I take away resistors in parallel, the equivalent resistance increases. So let's say that I have this resistor right here, and I take it away. Right, it goes away. And I want to know what happens to the voltage here. What happens to the voltage across this resistor? So what happens when I take that resistor away to the equivalent resistance of this little piece of the circuit? It gets bigger. Resistors in parallel, when an electron comes to resistors in parallel, it sees a bunch of different paths. And if it sees a whole bunch of paths, then that's not a very big resistance. But if you start taking away those paths, then that electron is going to face greater resistance. So if I take away this resistor, that increases the resistance of this side. Okay? So that means that the voltage here across this part of the circuit is going to go up or down. If the resistance goes up, what happens to the voltage? You know, it goes up. Remember, V is equal to IR. So if the resistance goes up, that means that the voltage is going to go up. Now the current's going to change too, but I still have to get the same amount of voltage that I had here. Okay? So my voltage here is going to go up. So what's going to happen to my voltage here? If this voltage goes up, what has to happen to this voltage? That's right, it has to go down, because they're still going to add up to equal this value. The sum of them still has to remain the same. All right? In parallel. Right. Now, if I take away a resistor in series, then the resistance will actually go down. But when you're taking away resistors in parallel, the resistance goes up. Okay? Let's imagine another one. So let's say, now I add a resistor over here. So if I add a resistor there, what happens to this voltage? Well, if I add a resistor, what happens to the equivalent resistance here? It goes down. And if the resistance here goes down, I've added more paths for the electricity to take, so that resistance goes down. If I do that, what happens then to the voltage? It goes down as well. So that means this voltage must increase. Okay? I think there's a question like that. I don't remember honestly, but I think there's a question like that. But y'all don't shoot me if that's not the case. I'm not certain. All right. What else? All right, so look at some old tests and sort of scroll through, and then y'all can yell out.
Yeah. Do one where it's like the charge and you have to figure out what metal is the wire?
Oh yeah, yeah. You'll certainly see one of those. There is one of those on the test. Let's look at an old test. I think it's a pretty straightforward test, all in all. Well, shoot, I'm not seeing one here. Exam 3? Of which one? Oh, it should be exam 3. Sorry, folks. I'll just work through one. I'll just make up one. All right, so let's say that I give you a material and I give you an area. I say it's whatever, 1 meter squared, and I give you a length. It's equal to 2 meters squared, or 2 meters rather, and I tell you a voltage, that it's a voltage of 10 volts, and that when I run this voltage through this material, I get a current equal to 5 amps. And then I ask you, what is the material? We worked through something like this in class. You'll see one like this, by the way. And I just want to know, what is the material? I'll give you a little table with a bunch of different resistivities. The first thing you have to do is find the resistance. R is equal to V over I. That's 10 over 5. That's 2 ohms. So I know that this resistor, this material that has a length of 2 meters and an area of 1 meter squared, that it has a resistance of 2 ohms. And then I say, well, I know that R is equal to rho L over A, and I solve this for rho. That's R A over L. So that's 2 times the area, which is 1 meter squared, divided by the length, which is 2 meters. And so it has a resistivity equal to 1. And then you would go through and look at your metals and look for the one that had a resistivity equal to 1. It wouldn't be 1, obviously, because resistivities are really small. But something, it would be in that effect. Does that answer your question? That's a good question. Make sure you're prepared for that you're able to do that. There's old test questions. I'm pretty sure there's a homework question like that, too. All right. Let's look at any of these questions in particular, y'all. This one right here? Yeah, so here, can y'all see that in the back? You can see it? Okay. It says the plate areas and the plate separations of 5 parallel plate capacitors are given. Capacitor 1 has an area A and a separation D. And don't forget that capacitance is epsilon naught A over D. There's no mention of a dielectric here, so I'll just leave that out. Capacitor 1 has A and D. Capacitor 2 has 2A and 2D. Capacitor 3 has 2A and D over 2. Capacitor 4 has A over 2 and 2D. And capacitor 5 has A and D over 2. And I ask you to rank them. So you just have to simplify these fractions. This is A over D. This is A over D. So I'm looking for one that has 1 and 2 tie. So these two go away. And this one. So I'm looking at either A or C. This is going to be 4A over D. This is A over 4D. And this is 2A over D. So which of these is the largest? 3 is the largest, so C is the right answer. Right? Just knowing this relationship, and then you have to rank them in order of their fractions. That's a good intent type question to do, actually. Those types of things. All right. Can I clear this up? I think we covered all of this, but anything in particular? Right now. I'm fine, I'll let y'all go. But any questions though? I want to, we have a few minutes if y'all want. Okay, folks, so the food drive is ongoing. If you haven't participated, then have it till Monday so you can bring things to the test. We're getting pretty close. We have about 500 or so right now. So, but if you want to bring in, some stuff on Monday, I fully expect that we'll get the maximum. But I really love to have y'all participate too. Okay? Y'all have a good day. See you on Sunday. Remember, auditorium, but I'll send an email out this afternoon.